Hey guys, welcome to your lecture on honors topic number 7, limiting reactant and percent yield. So this is not going to be very different from what we've been doing in class. The math and stuff is going to be the exact same as all the other stoichiometry we've been doing. We're just adding like a little level of complexity to it. So the scenario here is like if I have a reaction and there's multiple reactants, multiple things on the left, and I put them in a flask together and I say, okay, go make your products. In reality, unless we like have a very perfect situation that we like planned ahead for, most of the time we're going to end up like one of the things is going to get used up faster than the other. And we're going to get left with one of them left over, one of them running out. We're going to end up with a limiting reactant and an excess reactant is the vocab for that. So a limiting reactant, that's what the term we use to refer to the reactant that runs out first. AKA it's the one that is going to limit the amount of product we're actually able to make. Okay, so if one of them is limiting, one of them is going to run out. Your other reactants, you're going to end up with some that are left over, and we call those the excess reactants. So those are the reactants that don't get used up. AKA we're going to end up with them left in excess. Excess just means like extra, so the one that we have extra of, that is our excess reactant. So like, let me give you a little scenario here. So we're back to sandwiches. If this was a beautiful recipe for a sandwich, and to make one sandwich, I need 2 bread, 1 tomato, and 1 cheese. 3 bread, 2 tomato, and 3 cheese. How many sandwiches can I actually make here? So think to yourselves, how many sandwiches could we actually make? And you might be thinking, okay, well, if every sandwich I make, I'm going to need 2 bread, 1 tomato, and 1 cheese. And okay, so that would be 1 sandwich, 2 bread, 1 tomato, 1 cheese. If I went to go and make another sandwich, I'd go and want to grab 2 more bread and realize, I do not have enough bread. So in this scenario, we do not have enough bread to make a second sandwich. We're going to run out of bread. So that is our limiting reactant. So because I only have 3 pieces of bread, this reaction is gonna stop at just one time. I am only able to make 1 sandwich, and that's all I'm gonna be able to make. I'm not gonna be able to make that second sandwich. So after I make 1 sandwich, I end up with these other ones being left over. My excess is gonna be these guys. And I don't know, like imagine if you tried to make like half a sandwich, like yeah, we could use up one of these breads, but we'd still be left over with the other ones. These ones are gonna be our excess reactants. The ones that aren't gonna run out as fast. Okay, so that's the situation. So the way I'm gonna suggest you approach these problems, other people have different strategies, but the way I like doing these is just doing a stoichiometry problem, those calculations where we figure out how many of one substance can you get with this much of a different substance. Just do those calculations in regards to like each reactant. So like I'll show you what I mean, but the way I like to do it is do 2 separate calculations where you assume different reactants are limiting. So I'll show you what I mean by that, but basically we're just going to do the math as if I have this much of one thing and plenty of the other, and then swap it, this much of one thing and plenty of the other, how much could I make? And we're going to see like which one is going to show us it's going to run out first. So sorry, I don't know if I'm making that much sense right now, but you'll see. So basically like what everyone else, like our CP level problems have been doing, we've basically been assuming that I have excess, I have plenty of my other reactants. So like in CP questions, I've been giving you like, okay, I have, like looking at this next one, I wouldn't address the second reactant like in the CP questions so far. I've just been saying, okay, I have 1 gram of this thing, how many of this other thing can we make? And so like when I give you those questions, I'm assuming that everything else works out great. We have plenty of the other reactants. We're just getting like a theoretical, how much could you make? But at this level, what we're going to be looking at is, okay, in this situation, I have 1 gram of silver, but I also have 1 gram of iodine. And then the question is asking, how many grams of silver iodide could we actually make? Okay. So we have these 2 different reactants, and we're asking how much product we can make. So you might, like, I don't know, some people do different things, but in my brain, there's really not much of a shortcut for this. Like, because it looks like, okay, we have 1 gram of each, like, we should use up the same amount at the same time. But, like, because we have mole ratios, because in this reaction we're using up 2 silvers and 1 iodine, like, we're not actually going to be using them at the same rate. They're going to run out at different times. So the way that I like to do that, the way that I like to do the math, is just, like, assume each is limiting. So I'm going to first assume silver is limiting. So assume silver limiting. Okay. So what I mean by that, we're just going to do the problems like all the ones we've done in class, all the stoichiometry problems that I've showed, like CP level. So just say, like, okay, I have 1.00 grams of silver. How many silver iodide can I make with that? So we're just going to go through our stoichiometry process. Again, please practice this on PS 4.5, look at your map, etc. We're going to change our moles into, our grams into moles using our molar mass. Now we have moles of silver. To change it into moles of silver iodide, I'm going to cancel moles of silver. I messed up. I'm going to use my mole ratio from my equation. 2 moles of silver to 2 moles of silver iodide. And the question is asking for grams. So when I do it, I just solve it like for what the question's asking for. So I'm going to solve for grams. 1 mole AgI is 234.77 grams AgI. Multiply all across, and you're gonna get, oh god. I don't know why I erased. Okay, that's fine. You would get this many AgI. Okay, so just you solve a stoichiometry problem assuming that the other thing doesn't exist. You just assume, okay, I just have 1 gram of silver, how much could I make? So you do that, and then you swap it around. You assume, okay, what if I just had 1 gram of iodine? What would happen? So, you know, if you want more practice with this, you could try it on your own first instead of just watching me. Would be a good idea, but I'm just going to walk through it. So starting with our 1 gram of iodine, changing it into moles using molar mass. Converting it into silver iodide from our balanced equation. And finally changing it into grams because that's what the problem asked for. So if I multiplied all across, I would get this many silver iodide. Okay. So that is how I approach these problems, just doing like 2 separate math problems, 2 separate stoichiometry problems, and then to assess what we get out of this. So on our top part, it says, like, okay, up here, if I assume Ag is limiting, that's how much silver iodide I can make. And over here, if I assume iodide is limiting, this is how much I can make. So we want to decide which one is actually the limiting. So limiting means it's going to run out first. It's going to be the one that will create the least amount of product. So kind of like our sandwich example, like we're only able to make 1 sandwich because we ran out of bread. In this case, we're only able to make this much silver iodide because we ran out of I2. It was limited by the amount of I2. It's a smaller number than if we did it the other way. So this is our actual amount produced. And so generally when I do it, I just box that one, like that's how much I actually made. And you know, if I was to if I wanted to label which one was which, I2 was limiting. I just don't have space, but limiting reactant. And our silver was excess. So if I was to like if this was like an actual reaction we would do, you'd probably see some pieces of solid metal left in your reaction because not all of it reacted. So some of you guys had noticed that in like other reactions we've done, you like noticed that there was some leftover reactant. So this is why we're not actually using all of our reactants because one is running out. So yeah, that's the process. It's a little bit tedious. It's just math. Like it's just a bunch of math. So same dealio. Here it tells me I'm asking for moles of copper metal, and my starting stuff is 5 grams of iron and 10 grams of copper chloride. And something like I tend to just like making notes to myself on my reaction. So I have 5 grams of this. I have 10 grams, 0.0 grams of this. And I'm asking for this one in moles. So I tend to like to do that just to keep myself organized. So same dealio. If you want to try this one on your own, I recommend it, but I'm just going to crank her out here. So assuming these different ones are limiting, so I'll start with iron. So solve the problem, assuming all we have to care about is that I have 5 grams of iron, and go along until we get moles of copper. So I'm going to want to change this into moles. Then I can use that to translate into my moles of copper from my balanced equation. And if I was to plug that into the calculator, I think we would get that 2 sig figs. If I was to do it the other way, if we assumed this one was limiting, Hopefully your hands are hurting like mine. We can be in this boat together. And from my balanced equation, 3 moles of each. Changing into moles of copper, canceling out moles of copper chloride. And what I would get out of this one is 0.0744 moles copper, 3 sig figs. Cool. So, looking at this. So how much copper could I actually make? How many moles of copper are actually going to be produced by mixing together 5 grams of this and 10 grams of that? So you're looking for your smaller number. You're actually going to be able to create this many moles of copper, which is interesting. So you can't just look at, okay, we put 5 of that and 10 of that, but actually the 10 grams ran out faster because we have all these other like ratios at play. So, you know, it's hard to like predict in your head. Like I never try to play that game. I always just like do my math and see what I actually end up with. So in this case, the copper chloride was limiting reactant. Oh, side note, some people say limiting reagent. It's the same thing. But if you're watching like a video or something, limiting reactant, limiting reagent, same thing. Cool. So stoichiometry math, see which one's smaller. That's how much you can actually make. Whichever one you run out of first, whichever one makes the smaller thing, that's what the limiting was. The other one is left in excess. Okay, so that's that. Not too bad. It's just math, or, you know, it's just a lot of writing, but should be a similar process to what we've done before. So if you have your stoichiometry math down, it shouldn't be too bad. Okay, so our second concept for here is something called percent yield. Okay, cool. So what we've been doing so far, the like math we've been doing and calculating how much stuff we can make, that's all actually a theoretical yield. So just like based on math, like in a perfect world, how much could we make if everything works out and the mole ratio is perfect? How much could we make? So that is actually what we've been doing so far, is theoretical yield. The amount of stuff, amount of products. Created by a perfect reaction. Okay, but spoiler, very shocking. Science in the real world is not perfect. It doesn't work out that way. So very rarely are we going to actually have a theoretical yield. So you might be thinking like, oh, well, like, why not? Like, why wouldn't it just like do it? Me too. I've wondered that. But there's lots of stuff that could go wrong. Just to name a few. So like there's things like side reactions. So we'll never talk about that in this class, but like, what if the stuff you're making then reacts with like something else, or like there's actually multiple steps within the reaction that we don't actually see. There could be stuff going on with that makes it so we don't actually get all of our product. We could have imperfect conditions. And this is just, you know, to give some context. Conditions. Yes. Some reactions like are reversible, so like you make some product but then it goes back, which is super cool and fun if we're trying to make a product. There could just be impurities, like if everything's not perfectly sterile, or if like there's some residue in your glassware, or if something reacts a different way, or if your reactions aren't perfect. or, you know, there's just like so many things that can go wrong. Any scientist will tell you, like, it's just frustrating. Like, and like when I worked in a lab, it would always be like just the science not being nice today. Like, for me, like the cells wouldn't grow all the time, and you know, I did my best, and sometimes they just wouldn't grow. So you know, there's lots that can go wrong. There's lots of reasons why this happens, and it's really hard to nail down the like perfect reasons. It's a lot of times ends up being like guess and check of like what's gonna make it go better. But long story short, we're pretty much never going to get our theoretical yield out of a real life reaction. So what we actually get is our actual yield. So that is the actual amount, the real amount of product created. So it's kind of similar to like efficiency. Like, it's not exactly the same, but kind of like that. Like, how much, like, different reactions, and depending on, like, how someone does it, like, you're going to get different amounts of product out, even if you expected a certain amount out. So kind of same concept. So there's a very simple equation for this. Percent yield, it's just a percent, so it's our actual yield over our theoretical yield. Oh, I've been spelling it the wrong way on all of my notes. That's super cool. Okay, it's fine, it's fine. Yield. All of this is staying in. That's fine. Theoretical yield. Okay, and it's a percent, so you're gonna have to times it by 100 per use. So hopefully this math will look like pretty similar to stuff you've done in other classes. Shoot me an email, or I'll post, you know, let me know if it doesn't click, but it should be similar to other percent math you've done in math class. So like, here's an example. So this is the same reaction that I gave you up there. So I said that I'm gonna add a gram of silver and a gram of iodine gas to a flask. And up here, we calculated that we should make this much. So this thing we calculate, the like amount you think you're gonna make, the proper word for that is actually a theoretical yield. So from up here, my theoretical yield for this reaction was 1.84 grams of silver iodide. So on a problem where you haven't already calculated it, you'd have to calculate your theoretical yield, but it is just the math we've been doing. So the theoretical yield is what you get from your stoichiometry calculations. So that's my theoretical. But it says here that once I did the reaction, I actually only got out this many grams of silver iodide. So that is my actual yield. Sorry, not great placement. You can write it somewhere else if you want. So it's asking for my percent yield. So if I was to plug this into my handy dandy equation, so, oh no, it's fine. Oh god, cool. So if I was to plug into this thing those different numbers I have, so plugging in my actual yield to the top, so 1.550 grams on the top, and then putting my theoretical, which I calculated above, on the bottom, and then I'll have to multiply the whole thing by 100%. And I haven't actually done this, so let me do that. And of course, I don't have a calculator, so great, give me a second. So 1.5 divided by 1.84. 3 sig figs, your answer should be 81.5%. So yeah, pretty straightforward. theoretical is a calculated value. Actual is what you would actually measure in a lab situation. So I'm going to write that same equation here. So it's going to be the same deal. So then we'll have to figure out what we're going to plug in here. Oh, wait, just kidding. Sorry. Didn't even read my own problem. Okay, so this question, we should always read the problem first. We got that I mixed together this much iron and that much copper. So this is the same situation as what I did up here. So up here, what we calculated earlier is actually my theoretical yield for this question. So I'm going to copy that down here. This is my theoretical yield. And the problem says that we actually found out that this reaction is going to have a yield of that many percent. So then it's asking how many copper did we actually make? How much copper did we actually make? So there's different ways you can do this. If you are a whiz at math, you probably can think of, we're just going to multiply the number by a percent and get that out. If you want to do it that way, that totally works. I'm just going to show plugging it in just in case that is a helpful strategy for some of you. So if you have another way of doing it, you're welcome to do it that way. But just to show you, we could do it this way. So I'm just going to plug in the numbers I know. So I know that there is an 87% yield. 87%. And I know my theoretical yield was what I calculated above, 0.0744. And what I don't know is my actual yield. So I'm going to throw, I don't know, there's an X right there. So I'm going to throw a Y and we'll solve for it. So just some algebra, you could rearrange this thing. Divide by 100 and then multiply over your theoretical. So if this is like a helpful way of thinking about it, you could do it this way, and you could solve for the actual yield. Should be 0.085 moles. So again, if you've thought of a different way to do that, that's totally fine. But if you like seeing equations written out and plugging them in and algebraing it, that's also a strategy. So yeah, that's that. So theoretical yield, just a way of calculating how much, limiting reactant, a way of calculating how much stuff we're actually going to make, which things are going to run out. Theoretical yield is that calculated value that we get out of those calculations. But in reality, things aren't perfect, and we usually end up with a percentage of what we think we're going to get out. And you can do math like is shown right now to figure it out. So yeah, that's it for the lecture. So go ahead and try out those practice problems. Should be pretty straightforward. And let me know if you have questions.